All right. Today's lecture is topic 4. We're going to mainly focus on the Carnot cycle and the second law of thermodynamics. Now, the Carnot cycle is effectively a heat engine which you can transfer to the refrigeration cycle. It is this introduction to refrigeration, and as I've been saying, refrigeration is one of the most important things that we'll be covering, and also you will learn, because it's one of those future technologies. You have automation, refrigeration, and automatic refrigeration, transfer of food, storage, that kind of industries. We'll define the efficiency of a heat engine. So these are the learning outcomes for the whole topic. Define a Carnot cycle, we'll sketch the cycle on the thermodynamic diagram that tends to come up in your exams. Calculate the efficiency of a Carnot cycle in relation to fixed reservoir temperature. The second law of thermodynamics, and the first and second laws of thermodynamics using the heat engine. The Kelvin-Planck statement of the second law, and Clausius statement of the second law. And you'll see how to drive the Clausius inequality. This is the kind of thing I'll use in the future. And need for an additional thermodynamic property called entropy, which is topic 5. The first law is when you quantify energy. Energy can be quantified. This is energy in equals energy out. Whatever energy you put in, you'll have to get out. So it's your total energy equals potential kinetic internal heat. That equation effectively. Irreversible processes. These are spontaneous in one direction, but they can't go back. It's your house catching fire. It might not be that spontaneous, but you can't really unfire your house. The first law, the first law doesn't actually explain irreversibility, so that's why you have the second law. And also, second law covers inefficiencies. And we know that energy cannot be destroyed, but it cannot be completely converted either. That's your inefficiencies. This is the second law of thermodynamics. So the culprit is readily found apparently, and it is heat, because you do use a lot of energy as heat in the form of friction, and actually the change in chemical properties, physical properties, the PVT. So imagine Yoke-san. He is a wingsuit jumper, crazy Norwegian. And if he's at the top of the mountain, or in his case, this little red thing, which is on top of a mountain, he starts with potential energy. He's got a specific amount of potential energy at that point. When he jumps, he starts converting this potential energy to kinetic energy. Now, in reality, there's a limit to this kinetic energy where you reach your top speed, where the friction of the air slows you down. In reality, not really covered in this course. And you're converting that kinetic energy into heat while coming down. Now, if he hits the ground, because his parachute doesn't open, that whole energy is converted to heat. And you can't really get that heat back. In theory, there's a principle where you can get the heat back, but in practice, it is impossible. Now, of course, if his parachute opens, it converts to heat in the form of friction with air. So we prefer his parachute open. It could be imagined that some clever machine might convert this heat back to other forms of energy, even completely into work. So such a machine is called a Kelvin-Planck machine. And from experience, it's impossible. But it's just a principle that is explained in the form of Kelvin-Planck machine, the first time Kelvin and Planck theorized the idea. So consider a cup of tea, which will cool down until it has reached the temperature of the environment. The heat is transferred from the hot tea to the cold environment. So the internal energy in the tea at the high temperature is transferred via heat into internal energy of the surrounding. So you're transferring delta U from the tea to delta U to the air, and the delta U equals Q plus W. In this case, there is no work done, so it's just Q. Heat is being transferred spontaneously down a temperature gradient. So the T is hotter than your air. I know the principle is quite simple, but remember, in real life systems, you can only move from hot to cold. You can observe such a system for more than a human lifetime. I mean, you'll never observe the opposite process. Now, there's quite a few claims out there that says you can, but so far none of them have panned out. Now, if you can do the exact opposite using a machine, that machine will be called the Clausius machine. So you have the Kelvin-Planck machine and the Clausius machine. So heat back into work is Kelvin-Planck. Going from cold to hot is Clausius machine. Heat has a lower quality of energy. So as the quality of energy decreases with temperature. As the temperature dies down and is reduced, the quality of the energy is reduced. So imagine the quality being the more heat you have, the more energy you have, the more you can convert. And then the colder it gets, the lower quality gets higher. And just anything. The quality of energy, the Kelvin-Planck machine and the Clausius machines are equivalent statement of the second law of thermodynamics. So it says you cannot have 100% efficiency, that's Kelvin-Planck, and you cannot have a transfer from a cold body to a hot body. That's your Clausius machine, and that's the second law of thermodynamics. Using the first law, you can predict the direction of the process. Spontaneous and irreversible or reversible are simply impossible. So some reactions are spontaneous and irreversible, your house catching fire. Some are reversible, chemical reaction, or simply impossible, turning lead into gold. Actually, that's technically possible now. So the Kelvin-Planck and Clausius machines are actually the same, because they're explaining the same thing. Heat converting to work and cold to heat. These are in cycles. They're sequences of the process. The working fluid undergoes a series of thermodynamic changes, but after each cycle, the fluid is returned to its original state. That means you have let's say you have this cycle, the Carnot cycle. You can evaporate or you can heat something up, then you can cool it down. There might be a phase change, but by the end of it, there is no chemical reaction. So the full cycle covers all the phase changes, and at any one point, it will come back to the original state. And the working fluid can exchange heat and work with its surroundings. And that is the principle of your Carnot cycle, your refrigeration. You always want to exchange heat and work. So this is a vapor power cycle used to generate electricity. You have heat in. You're boiling water from the boiler. You boil the water, you form steam at higher pressure. It goes to a turbine. The turbine expands, and you excavate the energy in the form of work from the turbine. Now the steam then continues into a condenser. You remove the heat from the condenser, convert to water, use a pump it back into the boiler, and that is your full cycle. So at any one point, your water changes phase into steam, continues around the cycle, and then converts back to water at any one point. So always circle of life. So this cycle consists of high pressure, high temperature steam boiled. The heat from Q1 is supplied to the steam, so no shaft work is done. The steam expands through a turbine, and shaft work W3 is done by the steam as it expands, and assumed to be an adiabatic process. The steam is condensed back into a low pressure liquid, water in the condenser. mentioned. Heat Q34 is transferred from the steam to the cooling water, so you're recovering the heat always, because you don't want to waste anything. No shaft work. And the cycle is complete when the liquid water is pumped back into the boiler by the feed pump. So work for one is done on the water to raise the pressure from condenser to boiler pressure. This process is considered adiabatic as well, and there is no heat that is transferred. The working fluid, which is steam and water in this case, never leave the system. Each complete the cycle, the working fluid returns to exactly the same state as I mentioned. And the cycle, within the cycle, heat is supplied to the boiler, Q12, which is positive. The condenser releases the heat, so Q34 is negative. And the feed pump requires energy, making W41 work for 1, which is positive. Work is done on the system, and the turbine releases energy, so work is done on the environment, and hence it's negative. An important thing to note is the net work extracted from a given amount of heat supplied to this cycle Q12. So there is a net work for the full cycle. That's the amount of work you'll do, and you can extract. After each, and we'll get there by the way, after each cycle, the system behaves as a closed system. So this is the first law for the cycle, and it may be written as your Q in, your Q out, plus the work in and the work out. And you have a net Q and a net work. So all of that in a completely efficient system will equal 0, and your net work will equal your net heat exchange. So the amount of heat you put converts to 100% work, 100% change in energy. So the first law shows that the net work must be equal to the negative of the net heat. This is the definition of a heat engine, mathematically. There's a better version than that. So the heat engine does not only extract heat from the thermal reservoir, the boiler here. They always need at least a second reservoir that must be at a lower temperature. In this case, is the condenser. So you have your heat. It needs to be. You need to remove the heat so you can go back to your original state, or you're not going to transfer any energy. Now, when you remove the heat in the form of from the condenser, you can recycle that heat back into the boiler through another heat exchange, or by boiling that steam, or using that as a heat transfer. Your heat transfer liquid. That's called. What is that called? It's a form of energy optimization, and you're going to study that in fourth year anyway. I'll remember what it's called in a second. So the lowercase q and w are molar per mole. So the working fluid that has passed through one complete cycle. This is the per mole amount of heat and per mole amount of work done. So for the heat exchanger, the process is isothermal, because it's for the heat exchange, because you're assuming your temperature remains constant. You're constantly removing that heat, so the temperature is constant. So it's only your Q that is changing here. You're removing the Q in the heat exchanger. The other two remain adiabatic. So when you're compressing, you produce, it's delta U equals Q plus W. So you're producing Q and you're producing W, but there is no heat transfer. So your Q is 0, but you're still producing that heat, and it converts to work. Now you can because there is internal heat in the form of internal energy, you need to remove that heat somehow. This also applies to your multi-stage compressors. So when you compress, it heats up. That's why you remove it to have better efficiency. And this is the PEB diagram for a Carnot cycle. The net work is the sum of the individual volume work items in the cycle. So work 1, 2 plus 2, 3, 4, 3, 4, and 4, 1, the full cycle. And you need to note that there is no net fluid work. So the same results will be obtained using the volume work, or shaft work contributions. So your Q net, your total energy transfer, is Q12 plus Q23, 3, 4, and 4, 1, the full cycle again. And they equal, net work equals negative Q net. The first law must hold for each of the individual processes that make up the cycle, and also for the entire cycle. So some of these are zero and adiabatic, so it needs to hold for the whole process. So that's why net work equals net heat transfer. Since after each complete cycle, the working fluid returns to its initial state, there cannot be any change in internal energy. Hence, net work equals minus Q net. So your total internal energy, change in internal energy equals 0. So delta U equals Q plus W. Since delta U equals 0, total net work equals the negative of all the energy transferred. This is an ideal process. This is exactly the same results for the real cycle, since all processes in the cycle are unknown. And then the total net may be found by investigating each process individually. So the only difference with the real process is efficiency. And we'll get there as well. So the total work of the system is RT, the change in temperature, log of P2 over P1. That's your volume work. And for 3-4, RT log of P4 over P3. So it's similar to your compressors again. And the process that are isothermal have their volume work given by work done, W12 equals negative Q12 equals negative Q heat. So the change in the exchange of heat. And W34 equals negative Q34 equals negative QC. So the exchange is, one is hot, one is cold. So one is your boiler expanding, one is your condenser condensing, cold. The other two processes are adiabatic. So work contributions are your adiabatic work contribution. It equals negative RT over gamma minus 1 multiplied by 1 minus P3 over P2 to the power of gamma minus 1 over gamma. And this is single stage, so it's slightly different from your compressors. And exactly the same formula for work 4 to 1, because you're doing adiabatic work from in the boiler and back when you're converting to liquid. So your net energy equals negative Q12 plus Q34. This is the total change in energy. And in ideal systems, they cancel each other out because it's 100% efficient. Hence, your net work will equal W12 plus volume work for the process 3 to 4. So your heat exchanges cancel out. The amount of heat you produce, and or rather the amount of work you produce and the amount of work you put in equals the total energy you put in and the total energy you remove, 100% efficiency. So the net work depends only on the isothermal process and is independent of the work associated with adiabatic processes. And this shows that the work of the adiabatic process must be equal and opposite and must cancel, so that the work of 2,3 equals negative work of 4/1. The full cycle, the amount of work you put in should equal, because the heats cancel out because it's 100% efficiency. And substituting for the isothermal work input and input steps leads to the net work equals RT log of P2 over P1 plus RT C log of P4 over P3. I think the math is quite simple. It's just you're adding them. This is a diagram for a thermodynamic cycle, so almost pretty much a Carnot cycle. You put heat from a temperature source, you have your Qin, and you have your heat engine, you have your network out, and then you have the heat that goes through and you recover in the low temperature sink. This is your boiler and your compressor. Okay? So operating between two thermal reservoirs, and the nature of the cycle is irrelevant in this case, and only the heat exchanged and the network produced or used are relevant for a Carnot cycle. Efficiency of a heat engine is quite important and is defined as the energy out divided by the energy in for a heat engine. So the real energy out over energy in. And energy out is mechanical work and energy in is heat. So the amount of heat you put and the amount of work you return, and the amount and how much of that is converted. So this is no longer an ideal system. Network is important because it is the amount of mechanical energy delivered by the engine. Heat input is relevant because it costs money. And thermal efficiency, N of any heat cycle, is the net work over the Q supply. So this is where heat is wasted. Not everything is converted. So you can determine the operating cost using the efficiency. So if you know how much energy you're putting in, and how much work you're getting and how much energy you can get out, then you can calculate the cost of your system. An increase in efficiency are quite important, and they've been the principle of developing these heat engines. But there is a limit to the amount of efficiency you can have. Now, just so you know, it's the most optimum system, I think, is 64% efficient, but that's an impossibility to reach for a heat engine. So what's the barrier? The barrier is usually the amount of heat that is wasted, that is transferred from one form to another. So this was prompted by Carnot to understand what nature of this barrier was and how it could be overcome. Now we're going to go over that. The heat is supplied to any cycle and comes from the hot reservoir. So your total energy is your heat N, your network over your Qn, which is your network over the hot reservoir, the amount of energy from the hot reservoir. So using the net work, you can calculate the net heat, and based on that, you can calculate efficiency. So the amount of heat you got out over the amount of heat you originally have in your reservoir. So the amount of heat you recovered is your net heat. And your efficiency is the energy in the hot reservoir minus the the energy from the cold reservoir, in this case, in a power generation system, and that's your condenser, over the total heat. Makes sense, right? Just differences. And hence your efficiency is 1 minus QC over QH. These have a tendency to come up as well. Direction of the energy flows entering and leaving the working fluid, the system, and the first law for any heat engine can be given by the net work equals QH minus QC. Now, so in this case, they don't cancel out. Substituting this equation into the efficiency equation, and using the Carnot cycle, you get this equation. which is your works. So the work from the cold reservoir and the work from the hot reservoir. Yeah. And the Carnot cycle to be closed, we consider the Carnot cycle is closed. The pressure ratios for the isothermal process must be the same. So P2 over P1 equals P3 over P4. So the optimum system for an ideal, optimum ideal system. Same as your compressors. So simplifying the Carnot cycle, efficiency to the efficiency equals 1 minus Tc over Th. So the temperature of your condenser over the temperature of your boiler in a power generation system. Or your Carnot cycle, Th minus Tc over Th. So, efficiency of a Carnot cycle depends only on the reservoir temperature, based on the previous derivation, right? So, the absolute limit to efficiency of a Carnot cycle, and the efficiency is altered with the reservoir temperature. So, as soon as you change the reservoir temperature, you change efficiencies. And the hotter it is, the more efficient your transfer, because it's higher quality energy. And modern boilers operate at about 800 K, limiting the Carnot cycle efficiency to around 60%. And the cold reservoir is usually around 300 K. So the Carnot cycle is reversible because the isothermal and adiabatic process are reversible. It's a cycle, so you can always you have a reversible system. If it's not reversible, it's going to be finite, so you're not going to convert anything into energy. The Carnot cycle is when the Carnot cycle is irreversible, when one process releases some extra heat, some of the heat is lost. Heat can only go to the low temperature reservoir, and the Q supplied equals the QH of the irreversible process, which equals the QH of the Carnot cycle, which equals the total heat energy. Hence, the QC, irreversible, equals QC of the Carnot plus the QE, which is your supplied energy. Hence, your QC for an irreversible process is always larger than the QC for a Carnot cycle, because you have efficiencies to worry about. You have heat losses. This influences the net work by the first law. So the net work, which is irreversible, equals the QH of irreversible minus the QC of irreversible. Exact same process. Q net of irreversible equals QH minus QC of irreversible. And QC of irreversible is larger than Q of Carnot. Hence, the work of an irreversible process is smaller than the work of a Carnot cycle. So you convert less to work. You have less work done. Because the work is what you're looking for. That's what your output of your system. So therefore, the efficiency of a irreversible process is always smaller than the efficiency of a Carnot cycle. And with all practical cycles are irreversible. So all real life cycles are reversible. All the Carnot cycle itself is reversible. So you're always losing energy. You can never. It's not a perpetual machine. Factor in reservoir temperature limitation, so 800 K and 300 K plus irreversibility leads to an achievable efficiency of around 40 to 50%. And quite advanced systems like CCGT have efficiencies of about 60%. So these are combined systems. All irreversible cycles have a lower efficiency than their parent reversible cycles. And using reversible heat exchanger, so let's consider a reversible heat exchanger X that has an efficiency greater than the corresponding Carnot cycle efficiency. So, an impossibility. So your reversible X has more efficiency. So what you have from a hot reservoir, from the single hot reservoir, you have heat going in, you have work done by two engines. You have your Carnot and your, let's call it the X engine, and you recover that through a cold reservoir. Starting from assumption that the X is more efficient, and applying this to a definition of cycle efficiency, your net of X over H is larger than net of Carnot cycle, hence net of X, net work of X is larger than the net work of the Carnot cycle. So the engine X will produce more work than the Carnot cycle and therefore transfer less heat to the low temperature reservoir TC and then the Carnot engine. Now reverse the Carnot engine so that work and heat flows are reversed, but their absolute size stays the same. So your Carnot cycle, there's work being done on it, and it's going from cold to hot. And you have your X, which is a normal Carnot cycle. So if you put a boundary around this, you have work being done, you convert it into heat. The other one is a normal Carnot cycle. So it is clear, apparently, that the combined engine has no effect on the hot reservoir, and the combined cycle produces net work equal to the net combined equals net of X, net work of X minus net work of the Carnot cycle. Assuming that engine X is more efficient, it follows that the net combined is larger than 0. Hence, this means that work is produced and released to the surrounding by a combined cycle. And since the first law applies to the combined cycle and no heat is exchanged with the high temperature reservoir, the work must be produced from equal amounts of heat absorbed from the cold reservoir. So, for a system where you have a combined system, the combined engine is a Kelvin-Planck engine. So we covered this already. You convert into heat, then you convert heat into work. And it's thus impossible. So combined QC equals QX net combined. The initial assumption that engine X can have a greater efficiency than an equal Carnot cycle using the same reservoir must be incorrect. Yeah. However, can it be smaller? Well, yes. Following the previous process, but this time reversing engine X, resulting once again into the Kelvin-Planck, all reservoir engines operating between the same two reservoirs must have the same efficiency, hence efficiency of X equals efficiency of Carnot cycle TH minus TC over TH. In addition, if the reversible cycle operating between the same two reservoirs have the same thermal efficiency, then all the reversible cycles must be less efficient than any reversible cycle operating between the same two reservoirs. So less efficient than the reversible. The driving force for any heat engine, reversible or irreversible, is the same as the transformation of higher quality heat at higher temperature to a lower quality heat at lower temperature. And all reversible heat engines will extract heat in the same manner. So, and for reversible heat engines, it's exactly the same. So for a reversible, we're almost done. For a reversible heat engine, the energy quality overall stays constant. So moving heat from high to low temperature decreases the quality, but generating work from heat increases the quality. So when you increase the temperature, you produce higher quality system. These two effects balance out overall for a reversible engine. For a reversible heat engine, the energy quality overall decreases always. The two effects are the same as in a reversible heat engine, but an irreversible engine gives more heat to the lower temperature reservoir and generating less work. So if the maximum possible amount of work is not extracted, then the driving force will become non-zero and the cycle will be irreversible. So when you cannot recover all your energy, it becomes irreversible. The two classical statements of second law have already been introduced and applied. The impossibility of the Kelvin and Planck engine and impossibility of Clashes machine. It is now possible to investigate these two statements and show that although they appear to be different, they are equivalent to the second law. So the Kelvin-Planck statement of the second law is impossible to extract a system that will operate cyclically, extract heat from a single reservoir and then supply the same amount of network to the surrounding. So according to the Kelvin-Planck statement, the heat engine shown here would be possible, and such an engine could convert QH completely to double work network and at 100% efficiency. Such an engine would not need a low temperature reservoir at all. So you don't need a low temperature reservoir if it's 100% efficiency. So not really possible. And the impossibility of the Kelvin-Planck machine is consistent with the earlier idea that heat is energy of a lower quality. Work can readily be transferred completely to heat at any temperature, but the reverse is impossible. And it has also been shown that to transform heat into work it is necessary to transfer a sufficient amount of heat to a lower temperature. So you always need to transfer that heat. It seems that to transfer some heat into a higher quality energy, for example, work, a price has to be paid, so the efficiency, by producing a sufficient amount of lower quality heat. These two effects must either at least balance, so reversible case, or if not, the second effect must be larger than the first, which is irreversible. That is the end of it.